As we continue on with our Waltham 625 project, I have went ahead and disassembled the movement and pre-cleaned all the parts. Now, pre-cleaning is a step where the main systems that affect amplitude and rate are disassembled, all the jewels are pegged, and then the parts are run through the cleaning machine, whatever cleaning process you have. Pre-cleaning is very helpful because not only does it give us a clear view of the parts when we inspect them, but it also allows us to have more accurate results as we go through to troubleshoot for potential problems. Now, if you didn't see part one of this project, we started with a movement running 1200 seconds slow per day. And I showed you how to determine if the hairspring is correct for the balance wheel. Now, after sourcing a new hairspring, we ended up lowering our average rate to negative 102 seconds per day. But we're still carrying a delta of 666 and an average amplitude of 130. So we clearly still have a lot of work to do, but at least we have something to work with now. So if you haven't seen that one, I would recommend that you watch it before you start on this video. Now, in watchmaking, everything's important, but my main concern at this point is that amplitude of 130 degrees. Without having enough power actually getting to the escapement, and then the escapement being able to transfer that power as an impulse of energy to the balance wheel, nothing else really matters, right? So we're going to start with the powertrain in our inspections, and we're going to check to make sure that everything is running as free and smooth as possible. Now, there's a number of things that can cause a problem with amplitude here. One problem could be a bent or damaged pivot. We could have a broken jewel, or even a jewel that's sitting at a slight angle in its jewel hole, causing additional friction. There could be corrosion in the leaves of the pinions, causing additional friction as well. The actual wheel could be out of flat. So these are all things that we need to inspect and correct before we get to our final cleaning and reassembly. I'm going to start with the powertrain, and we're going to test each individual wheel separately to see how it performs on its own before we test the entire powertrain together. Now here you can see I'm testing the wheel for flatness. And if you look at the bridge in the wheel as I'll turn it, you'll notice the wheel rising up and going down. You can tell looking at it, the gap between the wheel and the bridge opens and closes. And that's basically telling us that the wheel's not flat. Normally, you would test a wheel on a pair of truing calipers, but it's impossible to find a set that has large enough holes for the actual pivots of a center wheel. So this is what I found the best way to check it for flatness. Now, before, when I was blowing the wheel to see how long it would spin, you'll notice that it didn't spin very long. So that could be caused by a couple different things. Usually what it comes down to is that there's wear on the pivot itself where it rides in the jewel. So we're going to take a closer look at that. Of course, we want to check our end and side shake, which is what I'm doing here. end shake is a visual check, right? There's no way to measure it. So what we typically do is we look at it and we compare one wheel to the next, right? So your barrel, which is the first wheel, should have the most, and then the second wheel should have about the same or a little bit less, and on down the line all the way to the escapement. I'm also looking at the jewel setting that's holding the jewel, and I have to admit it's not one of my favorite designs, but it is what it is. So we just have to work with what we got here. So now I'm just going to remove the wheel so we can inspect the pivots on this center wheel. Now when we look at the pivot and we look at the area between the shoulder and the end, right? This is the part of the pivot that runs inside the bearing, and the shoulder is resting on the bearing when the watch is in the dial down position. You can see that it's not shiny, right? It doesn't have any huge scratches in it, but this wear that you're looking at will definitely cause additional friction in the train. So we're going to end up polishing these because I want to get every bit of amplitude that I can in this old girl. And then as we look at the upper pivot, we can see the same type of wear. And this is basically caused by, normally it's watches that are running with dried lubricant that has grit mixed into it, or no lubricant, and people just continue to let it run because the hands are still moving. So those are something that we're going to have to address. And we'll be using our jacket lathe to burnish all those pivots. So now with the third wheel installed, I'm going to use my automatic blower, which I really like using for this process because I can get a really nice even speed from wheel to wheel pretty easily. And you can see I'm just watching the wheel spin, and you'll notice that this wheel is spinning for a lot longer than the second wheel did. So that's really telling us that that third wheel has straight pivots, which probably don't have any significant wear to them, even though we are going to look at it here in a second. And our jewels are even. So third wheel is we're in good shape with. Now as we inspect the pivots of the third wheel, you can see that the wear on the first side looked to be about what we saw on the second wheel, but on the top side it looks still fairly polished. So we're going to give them all the polish, but let's look to see how flat this wheel is now. Now with the third wheel mounted in our trilling calipers, we can turn the wheel and see that the wheel is flat compared to the index. So we have no problems here. So now we can move on to the fourth wheel. Also, after inspecting the jewels, they look good. So the third wheel in this train should be good to go. Now with our fourth wheel inspected, I'll hit it with the blower. It's kind of like putting it through a wind tunnel, what they do with race cars. But you can see we get a nice long spin. It did stop a little abruptly So we are definitely going to look at the pivots, and I'm expecting to see pretty much the same thing that we have seen on the other one. So let's check that out. Now, as we look at the lower part of the pivot, we can see that there is some wear. It's definitely not highly polished, but it's not very bad. And looking at the top part of the pivot of the fourth wheel, it actually looks pretty good. So we are going to polish it, but I don't think that we're having any issues with this wheel. But I do want to check to make sure that it's flat. So we have the fourth wheel in our joint calipers, and just turning the wheel with a artist brush and looking at the wheel in its relationship to the index pin, we can see that the fourth wheel looks to be pretty true. So I would say, other than a quick polish, that the fourth wheel is good as well. All right, so here we have our escape wheel mounted into the plate, and we can see that we're getting it spinning and it's stopping almost right away. So that's saying that there's just a ton of friction, because that wheel should be spinning very freely. So we definitely have a problem with the escape wheel. Now, as we look at the upper pivot, we can see that there is some wear. Visually, it doesn't look like it's bent, but we'll end up polishing this wheel or this pivot as well. But now, as we look at the lower pivot, we can see right up near the shoulder that there's quite a bit of wear there. So good polishing will definitely help get this wheel in better condition. Now, while I've got the wheel out, I want to inspect the locking corner of the escapement teeth. And what we're looking for is we want to check each individual tooth, and we want to make sure that the locking corner, which is what actually lands on the pallet stone, we want to make sure that that corner is nice and crisp. Any kind of wear right there will affect it as far as how well the escapement moves. So we just want to visually check them and make sure that there's nothing obvious. There's some other checks that we'll do later when we get into the escapement, but we want to just do a visual check now to see how they look. And I'm not seeing any obvious problems here. And now, with the escape wheel mounted into our joint calipers, we can see that the escape wheel appears to be flat. So that's a positive for sure. Now, unfortunately, as I'm inspecting the jewels for the escape wheel, I can see that the upper jewel in the bridge has a big crack in it. Fortunately, I do have some parts for the 625, so I'm going to first look to see if I have a jewel setting to replace the one that's cracked. When I measured the pivot hole for this jewel, it was 22 hundredths of a millimeter, but the only available stock that I have for this movement is a pivot hole that's 0.2 of a millimeter. So what we're going to do is we're going to reduce the size of the pivot on the escape wheel so that I can use the jewel setting that I actually have. Now, if you've never removed one of these jewel settings before. They're pretty straightforward. You know, obviously I took the screws out, and then it's just a matter of pushing it out. And in most cases, you can just take a piece of pegwood and push it straight out. Um, Sometimes if it's a little tighter, or there's some corrosion or something that's holding it in, you might need a jewel press. But now, since I've done detailed videos on how to use a jacket lathe, I'm just going to give you an overview here. So the first thing we need to do is measure our pivot, and then we want to select a pivot bed that's just slightly smaller than the pivot measurement so that it actually sticks up a little bit higher. This one is 19/100 of a millimeter. And you can see below it there's 2/10 of a millimeter and on and on. So the first thing we're going to do is select our bed of 2/10 of a millimeter. Then we're going to install our escape wheel onto the jacket lathe. And we'll lock that in place. Then we need to move our carrier up into the spokes of the wheel. And the carrier is what will engage with the spokes on the wheel to move the wheel back and forward as we're polishing it. Next, we have our burnisher, which has two sides. The first side with the microscopic grooves on it, this is the side that we use for polishing. And when I flip the burnisher around, on the other side is an extremely fine file. I believe it's a number 10 cut, but it is extremely fine, and that's what we're going to use first to reduce the size of our pivot. Now, I use my burnisher in my right hand, so I use a left burnisher. And just to clear up some confusion that I heard, the reason it's called a left burnisher is because the angle that's on the burnisher that rides against the shoulder of the pivot itself is on the left side of the burnisher. If you are left-handed, you would use a right burnisher because the part that you're working on the pivot is going to be on the right side of the burnisher. Okay. Now, traditionally, you would use a bow to power the jacket lathe, but what I use is a retractable ID holder that has a retractable cord that pulls in and out of its housing. And I use that. I find that to be much more effective to power the pulley. When you're working a pivot with a burnisher, you want the wheel and the direction that you're moving the burnisher to be opposite of each other. So depending on how you wrap the cord around the pulley will determine which way the pulley turns as you're pulling the cord. So you could see that here I wrapped it over the top first, then looped around. So when I pull the cord, the wheel is actually turning away from me. If you wrap the cord underneath the pulley first, now when you pull on the cord, the wheel is actually going to spin towards me, which is what I want. Again, the idea is that we want the wheel to be turning in the opposite direction that we're pushing the burnisher across the pivot. We don't want them going in the same direction. We want that friction to be cutting across the top of the pivot, and that's what's actually going to burnish it. Now, just in case you were wondering how I have this jacket lathe attached to my bench, on the underside there's two pins, and I just have two holes drilled into my workbench that those pins fit down into, and that holds it in place. And then on the other end of the bench, I have just a simple nail tacked into the bench where I can hook the loop um, on the string that I'm pulling, so that when I need to stop, I can hook it on there so it doesn't come unwound and the wheel goes flying off in some other direction. Now, as I file this pivot down, there's going to come a point where I have to stop because the pivot is going to be, right below the surface of the bed. And then all you do is you just drop down another bed size, and you just continue to do that until you're right around the area of thickness for the pivot that you're using. So somewhere between, 200ths to 100th of a millimeter is really what we're looking for. We want that pivot to be just about 100th or so smaller than the jewel hole. And then once we get close, then we're going to start actually burnishing and polishing those pivots. So I'll finish this up and we'll put it back in the movement and see how it works. Replacing the jewel is also pretty straightforward. One thing that you do want to be aware of is this groove or ledge that's in the jewel hole where the setting sits. So you want to make sure that that's clean, that there's no grime or dirt or anything like that in it. Otherwise, when you put the jewel setting in, it's not going to sit flush. So you want to make sure that's clean. Now, the replacement setting should just fit in, but sometimes if the tolerances aren't exactly the same as they were before, you may need to use a jeweling press to press it in, but it shouldn't take too much, and you just want to make sure that it's seated flat into the opening, so that it's not at an angle. And then once you're satisfied that the setting is in fully and that it's flat and flush, then it's just a matter of replacing the screws. Now that I've reinstalled the escape wheel, we'll test it again and see how it spins. And as you can see, it's spinning much freer now. So now we want to check the end shake of the escape wheel to make sure the divisions between it and the pallet fork are correct. Looking at the escape wheel and pallet jewel in the dial down position, we can see that the escape wheel tooth is slightly lower than the pallet stone, which is what we want. And now looking at it in the dial up position, we can see that the escape wheel is just barely coming down to the edge. So we're about as centered into that jewel as possible. Now, the reason you don't want the escape wheel hanging off of the pallet stone, obviously, is because that will diminish the impulse from it as it's moving the balance wheel. So in this case, it looks like we're good. If you're in the situation on this movement in particular where you need to make an adjustment to the end shake, you would do it from the jewel in the plate, not the one in the bridge. Now I'll go ahead and polish the second, third, and fourth wheel, and then we can test everything out. Today, you've just seen a glimpse of what my complete watch repair course has to offer. From mastering the basics to tackling complex repairs like this one, I'm there to guide you every step of the way. If you're ready to turn your passion for watches into a rewarding skill, then check out the link in the description for more information.